In 1971, for atomic clocks boarded ordinary passenger jets. They flew around the world, then returned to the clocks that had stayed behind. When the instruments were compared, they no longer agreed. The differences were tiny, billionths of a second. But they had the signs predicted by relativity. Motion had changed one clock. Gravity had changed the other. No mechanism had failed. No clock had lost its calibration. Each had measured the time along its own path through space-time. That is the mystery at the center of this story. If two accurate clocks can leave together and reunite with different readings, then time is not a universal river carrying everyone at the same rate. It is personal. It depends on where you go, how fast you move, and the gravity you encounter. We already know how to travel unequally into the future. The question is how far that fact can be pushed. Imagine two flashes of light, one sent from the floor of a rising spacecraft and one received at the ceiling. During the light's journey, the ceiling moves. The receiver measures a changed frequency. Einstein's equivalence principle says acceleration and gravity are locally indistinguishable, so gravity must change the rate at which clocks tick. A clock lower in a gravitational field accumulates slightly less time than one higher up. Motion creates a second disagreement. Light has the same measured speed for every inertial observer. To make that possible, distances and durations cannot remain absolute. Different observers divide space-time into space and time differently, while agreeing on the combined interval. This is not a trick of perception. A traveler's heartbeat, chemistry, and thoughts all follow the same local clock. Nothing feels slowed. The disagreement appears only when separated paths are compared. Relativity does not say clocks are unreliable. It says the route taken through space-time is part of what a clock measures. Now put those clocks into orbit. A navigation satellite moves quickly, which makes its clock run slower relative to Earth. But it also sits higher in Earth's gravitational field, where its clock runs faster. For GPS satellites, the gravitational effect wins. Engineers must correct the net difference, about 38 microseconds per day. That sounds negligible. It is not. Light travels almost 300 meters in 1 microsecond. Leave the relativistic correction out, and a positioning error would grow by kilometers each day. Every location fix is therefore a quiet experiment in curved space-time. Atomic clocks on the ground define the reference. Satellites broadcast carefully corrected time. Receivers compare arrival times from several spacecraft and solve for position. Relativity is not an ornament added to the system. It is inside the calculation that tells an ambulance which street it is on. Before asking whether humans can exploit time dilation, notice what has already happened. Civilization has engineered around the fact that clocks genuinely disagree.
Or like middle orbit. That is far enough away from Earth's source of gravity for them to have a measurably different space-time condition.
Oh.
So that their clocks tick faster than our clocks on Earth's surface. Because they're farther away, and
the effect is no longer confined to aircraft and satellites. Modern optical clocks can detect the gravitational difference between heights separated by millimeters. Raise one clock slightly and, in principle, it steps into a fractionally faster future. Laboratories compare atoms whose oscillations are so regular that losing a second would take longer than the age of the universe. At this precision, a clock becomes a sensor for gravity, elevation, and the shape of Earth. It also removes an easy escape from the evidence. Time dilation is not inferred only from distant stars or fitted to a complicated cosmological model. It can be measured across a laboratory bench. But a millimeter of height buys an absurdly small advantage. A human traveler needs a much larger separation between their elapsed time and hours. There are two known levers, speed and gravity. Both are real. Both become powerful only in regimes that are brutally difficult to reach. So begin with a cleaner route. Suppose we build a ship and make it move extremely fast.
Travel is absolutely possible, and this is not some sort of weird sci-fi thing that I'm talking about here. Albert Einstein taught us more than 100 years ago that time travel is possible if you're focusing upon time travel to the future. And I'm not referring to the silly thing that we all age, right? We're all going into the future. Sure, I'm talking about if you wanted to leapfrog into the future, if you wanted to see what the Earth will be like 1,000,000 years from now, Albert Einstein told us how to do that.
A spacecraft passes Earth at a steady speed. From Earth, its moving clock runs slowly. From the spacecraft, Earth's clock also runs slowly. That symmetry sounds as if nobody can return younger. The difference arrives when one traveler changes course. To reunite, the spacecraft must accelerate, turn around and enter a different inertial frame. Its path through space-time is no longer equivalent to Earth's. Draw the journeys as world lines and the answer becomes geometric. The proper time along the bent traveling path is shorter. At 90% of light speed, 1 year aboard corresponds to a little more than 2 years on Earth. At 99.99%, the gap becomes dramatic. A traveler could cross great distances while decades or centuries passed at home. They have not frozen time or broken the light barrier. Their own clock ticks normally. They simply follow a route through space-time containing less elapsed time. This is the twin paradox, and there is no paradox once the complete paths are compared. The equations permit the journey. Engineering makes it merciless. Kinetic energy rises steeply as a massive spacecraft approaches light speed. Each additional 9 in the velocity demands vastly more energy than the last. A vessel must accelerate its structure, shielding, fuel and whatever fuel is needed to slow down. Then interstellar space becomes hostile. A grain of dust struck at relativistic speed can release the energy of an explosion. Sparse gas becomes a beam of high-energy radiation. Navigation must anticipate hazard years before their light reaches the destination. Heat has to be rejected. Passengers need protection through long acceleration and deceleration phases. Even an ideal matter-antimatter engine would face storage and efficiency problems beyond present technology. None of this overturns relativity. It separates permission from practicality. Nature gives us a route into the far future, but it charges an extraordinary price in energy, materials, and risk. Could gravity provide a route that does not require racing across the cosmos? In principle, yes. The clock difference can be made by staying near something extremely massive. Picture 2 observers. One waits far from a massive object. The other descends toward it and hovers. Their clocks separate because curved space-time assigns different elapsed times to their paths. Near Earth, the effect is modest. Near a neutron star, it becomes serious. Near a black hole, it can become extreme. From far away, signals sent by the lower observer arrive increasingly redshifted and delayed. The observer nearby does not feel their own seconds stretching. Local physics remains ordinary. The disagreement appears when signals or reunited clocks are compared. This creates a genuine future travel scenario. Spend a limited time deep in a gravitational well, then return to a region where clocks ran faster. More external time may have passed than you experienced. But the word hover hides a problem. Remaining just outside a horizon can require enormous acceleration. Radiation, tides, and the accretion environment may be lethal. A rotating supermassive black hole offers gentler tides at its horizon, but it is still not a convenient machine. The geometry is real, the itinerary is not. What actually happens at an event horizon depends on who describes it. A distant observer receives signals that become weaker, redder, and more delayed. In simplified language, the falling object seems to freeze near the horizon. The falling observer crosses it in finite proper time and, for a sufficiently large black hole, may notice no sharp boundary at that instant. Both descriptions belong to the same space-time. The horizon is not a solid surface. It is a causal boundary. Beyond it, every future-directed path leads inward. This matters because black hole time dilation is often sold as a safe viewing platform for the end of the universe. Real black holes complicate that picture. They rotate, accrete matter, emit radiation from their surroundings, and eventually evolve. A traveler must ascend, survive, and escape before crossing the point of no return. Extreme time dilation outside the horizon remains permitted, but the closer the desired time jump, the more severe the required orbit, acceleration, and environment. Gravity can send you forward. It does not provide a return ticket to yesterday.
If a star's collapsing, then does it not freeze forever in some sense on the horizon? So all sorts of initial, early conceptual problems, which ultimately were solved. The thing about relativity, just the one sentence thing to understand, is that time can stop from one perspective, but time can pass at the usual rate from another perspective. And indeed, from the perspective of an astronaut falling into a black hole, then for a sufficiently large black hole, like the ones that we find at the centres of galaxies, the astronaut would notice nothing at all as they fell across the horizon into the interior of the black hole.
Forward time travel exploits unequal elapsed time. Backward time travel asks for something deeper, a path that returns to an event before it began. In relativity, such a route is called a closed time-like curve. Some mathematical solutions contain them. A rapidly rotating universe can. Idealized infinitely long rotating cylinders can. Certain cosmic string arrangements have been proposed. A rotating black hole solution contains strange causal regions in its maximally extended geometry. But a solution to Einstein's equations is not automatically a buildable object. It may require infinite structures, impossible initial conditions, unstable interiors, or matter arranged in ways nature never permits. The most intuitive proposal is a wormhole, a shortcut joining two distant regions of space-time. Wormholes emerge naturally as geometries worth studying, but no traversable wormhole has been observed. The familiar tunnel is a diagram, not a photograph. Even so, it lets us ask the backward time question precisely. If two entrances can be connected, can their clocks be made to disagree? And if they disagree, what happens when someone passes through? Start with two mouths, A and B, connected through a throat. Step into A and, in the idealized geometry, emerge from B without crossing the ordinary distance between them. That alone is only a spatial shortcut. Both mouths can still agree about time. To create a time offset, take one mouth on a relativistic journey or hold it deep in a gravitational field while the other remains behind. The moving or lower mouth accumulates less external time. Bring the mouths back near one another and their internal connection may preserve the earlier synchronization while their surroundings no longer agree. Enter the younger mouth and emerge from the older mouth at an earlier external time. Travel through ordinary space back to the first entrance and the path can close. This is the core idea behind a wormhole time machine. It uses the same measured time dilation that operates in atomic clocks and satellites. The speculative step is not the clock difference. It is assuming a traversable throat can exist, remain connected, survive the motion, and accept a traveler.
The future or to the past?
If you have wormholes, then if you move the mouth of one wormhole down near the surface of a black hole, time flows very slowly there compared to the rate of flow of time back here on Earth. And so the two mouths get out of sync. The mouth of the wormhole sits down near the surface of the black hole, and it sits there with only a few hours passing, while up here on Earth, 1 billion years pass. And so we on Earth can then go down through the wormhole and can come out near the surface of the black hole 1 billion years earlier. We can then come out and go back up into the external universe 1 billion years earlier than we went down.
Wormhole is near a black hole where time is ticking more slowly than where you came from.
Or if it was there for a while, once you set the time difference between the two openings, you can then move away from the black hole because the time.
An ordinary Einstein-Rosen bridge does not stay open long enough to cross. Its throat pinches off. Traversable designs require the geometry to flare outward, resisting collapse. In classical general relativity that typically demands negative energy density, often called exotic matter, quantum field theory does allow local negative energy effects. The Casimir effect, for example, changes the vacuum energy between closely spaced conducting plates. But this does not hand us a reservoir of negative mass. Quantum inequalities appear to restrict how much negative energy can exist, how long it can persist, and how it must be balanced by positive energy. A human-sized wormhole might demand quantities and arrangements with no known method of production. Then come stability questions. Radiation entering one mouth may be amplified as it circulates. The throat may react to a traveler's mass. Tiny perturbations could collapse the geometry. So negative energy is not a missing component waiting on a part's shelf. It is a sign that the proposal presses against the boundary between classical spacetime and quantum physics, where our theories are incomplete. Suppose the engineering worked. A message passes through the wormhole and arrives before it was sent. It tells the sender not to transmit. If the warning succeeds, where did the warning come from? The grandfather paradox is the dramatic version, but information alone is enough to expose the problem. One response is consistency. Perhaps only histories without contradiction can occur. Events inside the loop constrain one another so that every action was always part of the same history. That avoids logical contradiction but creates strange information loops, where a formula or object exists without a clear origin. Another response invokes branching quantum histories, though no accepted theory shows that a macroscopic wormhole must create branches. The safest conclusion is narrower. Closed time-like curves challenge the ordinary causal structure used by physics. They do not merely reverse a clock. They place causes and effects on a loop. A mathematical geometry can describe that loop locally. Whether the full universe allows it to form is a different, unanswered question. Stephen Hawking proposed that the laws of physics may protect chronology. As a time machine approaches the moment when closed time-like curves first appear, quantum fields could circulate through the nearly closed paths. Each circuit can blue-shift the radiation. The accumulated energy may grow large enough to distort or destroy the wormhole before causality fails. This is an appealing idea because the mechanism attacks the machine precisely when it becomes dangerous. But it is a conjecture, not a completed theorem covering every possible space-time. Calculations near a chronology horizon are difficult, and semi-classical methods combine quantum fields with a classical geometry exactly where quantum gravity may become essential. Some models show destructive divergencies. Others depend sensitively on assumptions and boundary conditions. The phrase chronology protection therefore names a serious research question, not a known cosmic police force. Nature may forbid backward time travel. It may restrict it to self-consistent histories. Or our current equations may be asking a question they cannot answer. To know which, space-time itself has to be understood at the quantum level.
Because you can skip, if you could skip beneath relativity, so to a deeper picture of space-time, I still guess that causality will be there.
Will still be there.
I'm not aware of anyone who's proved that, or I'm not aware of anyone's opinion on it. It is my opinion.
Yeah.
I don't think I have any evidence for that other than Stephen Hawking.
How is that different from Stephen Hawking's time travel conjecture?
Yeah, the chronology protection conjecture.
Sorry.
So it's called a conjecture because he conjectured it.
It was conjecture.
And that was his conjecture, you're right. He said that whatever the underlying laws of physics are, they have to prevent time travel into the past, which is to say that causality
protecting
is respected.
causality. Right, exactly.
But I think we're absolutely miles away. We're miles away. This might not be right, this idea of space-time emerging, although it's quite a popular research field. Mm-hmm. It is interesting because quantum...
General relativity treats space-time as smooth geometry. Quantum theory describes fields and probabilities. Both work extraordinarily well in their domains, yet they resist unification where curvature and quantum effects are simultaneously extreme. A wormhole throat, a black hole interior, and a chronology horizon live near that frontier. Candidate ideas offer clues. In some research, quantum entanglement and wormhole geometry appear mathematically related. In holographic models, space-time may emerge from deeper quantum information. Other approaches quantize geometry itself. None has produced an experimentally verified blueprint for a traversable time machine. This uncertainty cuts both ways. We cannot honestly announce that every backward time geometry is impossible. We also cannot use an unfinished theory as permission to assume one can be built. The burden of evidence remains with the machine. It would need a physically real geometry, a stable throat, controllable energy conditions, and a causal history consistent with quantum physics. At present, not one of those requirements has been demonstrated at human scale. The mathematics keeps the question open, the evidence keeps our confidence low.
About everything that fell in. But the implications of that, the mechanism by which that happens, I would say it's profoundly exciting, because it really does seem to be giving us a glimpse of a deeper theory of gravity. The simple way to say it seems that space and time are not fundamental. So one view, and I emphasize that there are other views, we're at the cutting edge of research now, but one view is a field which has become known as emergent space-time. So what does that mean? It means that space and time themselves are not fundamental. In Einstein's picture, we assume there is such a thing as space-time. This four-dimensional surface, manifold is the technical term, but you assume it. It's part of the model. There are such things as space and time woven together into the fabric of the universe. What they are, Einstein has nothing to say. It seems that there is a deeper theory underlying what we think of as space and time, which is a quantum theory. And so the idea is that space and time themselves emerge from what? From quantum entanglement, from some kind of smaller parts or pieces. We don't know what those things are. We don't know the nature of them. But it does seem that there's a deeper underlying theory from which space and time emerge. That is what we call the quantum theory of gravity. But the key thing to understand is we've been driven to that picture by asking very clearly defined, precise questions about how black holes behave, which goes all the way back to Einstein.
A credible discovery would not begin with a photograph of a glowing tunnel. It would begin with measurements. Astronomers might find gravitational lensing that cannot be explained by ordinary compact objects. Precision timing could reveal a repeatable path inconsistent with conventional propagation. A laboratory might demonstrate controllable negative energy configurations far beyond known quantum effects. A theory of quantum gravity could predict a distinctive, testable signature and survive experiment. Each step would need independent confirmation and a clear accounting of energy, stability, and causality. Until then, simulations are tools for understanding equations, not evidence that the represented objects exist. The same distinction protects the parts of this story that are established. Atomic clock redshift is measured. Relativistic particle lifetimes are measured. Satellite corrections are operational. Black holes are observed, though not used as transport systems. Wormholes and closed time-like curves remain theoretical. Keeping those categories separate does not diminish the wonder. It shows exactly where knowledge ends and where the frontier begins. So, could humans really travel through time? Into the future, yes, in the precise relativistic sense. We already do it by tiny unequal amounts. Speed and gravity change the proper time along a journey, and experiments agree with the prediction. Large human jumps are physically permitted in principle. A near-light speed voyage or carefully chosen path near extreme gravity could carry a traveler into Earth's distant future while they experienced much less time. The obstacles are technological and potentially lethal, not a known violation of physics. Travel into the past has a different status. General relativity contains mathematical roots, including time-shifted wormholes and other closed time-like curves. None has been observed. Traversability appears to require exotic quantum conditions. Stability may fail. Chronology protection may intervene. Quantum gravity may change the question entirely. The honest verdict is asymmetric. Forward time travel is real physics. Dramatic forward travel is an extreme engineering dream. Backward travel is mathematically conceivable in some models, experimentally unsupported, and possibly forbidden. The clocks have already opened the door. Whether nature allows it to swing the other way remains one of physics' deepest mysteries.